development. And I'll hand it over to you.
Hi, everyone. My name is Eldy Lazaro, and I'm coming from the University of Boulder in Colorado, the US, and I'm here on behalf of my research team that we've been working on this project for the last 3 years. Well, this is some of my credentials. Oops. Yeah, and this is the research team. I will start like with a story. This whole project started with my two co-advisors, Mirella and Laura, my PhD co-advisors, and Michael Rivera, who at the time was a postdoc in our lab. And we, at the time, were all interested into bringing sustainability into smart textiles. So as we all know, smart textiles is kind of a growing industry, and it's just like, well, a lot of money projected to be part of this industry. However, just to explain in some context, smart textiles are kind of like a combination of traditional fabrics with electronic components that are in a shape of conductive threads, for instance. They are either knitted together or woven together, and they are meant to behave as an interactive interface in clothing. So this is just an example. There is one in the market that it's, if you want to see how that looks like. But one of the downsides, I would say, or the biggest environmental challenges of smart textiles is that they are combining two big waste streams. They are combining textile waste with electronic waste. And electronic waste in a size that it's very, small. We are talking about threads. They are kind of inseparable. And one of the considerations that probably designers of smart textiles are not having is like, how are these two pieces are going to be separated at the end of life? So some approaches to that in the research community, but also like in the open source community, have been taking these design considerations of like disassembly and also repair to like at the textile structure level. And then some other prior work has been exploring into how to incorporate biomaterials, meaning, bio-based material like industry byproducts, and how to use them as a scaffold materials for embedding electronics. So then at the end of life of these, let's say, interactive devices or textiles, the materials can be composted and the electronics could be taken apart in this decomposition or breakdown of the material. So this all was very inspiring for what is coming next. And just to also give an overview of like where our project takes place, if we look at the smart textile life cycle, especially when we are thinking about sustainability, we need to see like the full life cycle of the things that we are doing. So in smart textiles overall, there are different approaches happening like in the smart textiles structure level, but we wanted to go back at the very beginning, which is fibers. Fibers are the backbone of textiles, and we wanted to see how could we bring some sustainable considerations in that particular phase. So that's why the desktop biofiber spinning is at the very top. So this was kind of the question that moved us forward in the research and work. What are the existing tools and fabrication workflows for making fibers? So I would ask the audience if you can think of any household equipment maybe that make fibers out of like any everyday materials. A dryer yeah, that's true. Cats make fibers, yes. What? Yeah, when we're combing our hair, well, yeah, that's true. Spinning wheel. Yeah, yes. So that all of the answers are correct, but something that for our team came to mind of like, how could we make fibers was using a cotton candy machine, right? Cotton candy machine makes fibers out of sugar. And because we were interested into using biomaterials or existing food byproducts from the food industry, we kind of tested with gelatin and kind of had this hypothesis. If we can make fibers out of sugar, maybe we can also make it out of gelatin. This material in there is gelatin. But this is what happened. It didn't turn into fibers, it just burned. So we kind of tried to, we hacked the machine, change temperatures, make things, but it didn't work. So we just got more burnt gelatin, but then we just saw a little bit of like fuzz of gelatin at some point. So this actually made us get into like, the scientist side, which is why one material makes fibers, why this other material doesn't make fibers. The answer is like basically sugar crystallizes, and that's why we get fibers. Gelatin, it's a protein. It doesn't melt in the same way as sugar, so that's why we don't get fibers at the polymeric level, let's say. But something that we found in these other research papers, that people spend like a whole PhD just coming up with like a recipe to make fibers, and this was a replication on one of those research papers, which is like we need to make the gelatin into a liquid. And then the liquid can be made into fibers. But we kind of failed with the cotton candy machine. However, when we got in a syringe and kind of pull it, we were able to get like these thin fibers. And you can see here some examples. This is one of our friends in the lab. So he was the tallest man, and we were like, could you hold it at the very top? And we will try to pull fibers. And we really got it. So we got fibers, and that was pretty cool. And at the end of the picture, you can see that we actually have to, let's say, coagulate the fibers. So then it cools down. And the coagulating liquid is actually isopropanol. So not very safe for the eyes to be spraying on a fiber that someone is holding. So this was kind of like the backstory of how we got to the machine that I'm going to show in a minute. And this was April 2022. So we got into like learning or also researching what are these existing tools and fabrication workflows that are made for fiber design, because we are probably all have a t-shirt that is made out of synthetic fibers, like, right? Acrylics and what is these other materials? Polyester, right? All of those are not natural fibers. They are made in a lab and they are extruded into like a long string, and that's how we make threads. So the reality is that all those fibers are made in machines like what you see on the screen. This is like a prototyping machine for a chemistry department. So I went on the summer of 2022, I went to ITA, RWTH Aachen in Germany, because they are known for just making a lot of fibers of different kinds of materials. And I spent the summer, and very naively, I thought, oh, I'm going to come with my liquid solution that we developed in the lab. We're going to put it in the machine, and then we're going to get a lot of fibers so we can bring it back to our lab and work with the smart textiles. The reality was that the machine is not designed to work with bio-based materials. They are designed to work with like more stable materials that don't need heating, for instance, to be able to be extruded. So something that I learned in the process was like there is a whole list of steps for material preparation. We were used to use 10 milliliters of material in the syringe to pull fibers. Here we need half a liter, 500 milliliters to just make one test. And one test can be done in a day. But then something else that you can see on the right, it's also that, I have some funnels. I wrapped the nozzle that you see in there with some foam, so the heat could stay there when the material is coming through. There is also, I don't know if you see here, like a coil, a wire, so it can keep the whole nozzle heated. So it was a lot of hacking. I'm so glad and thankful for the people in the lab that let me do this to their machine, because they are also very expensive machines. But the challenge is basically boils down to there is a specialized equipment that we need to know how to work with. We need to understand polymers and like how things work at the polymeric level, because like temperature and viscosity, all of those are really important to make fibers. These type of machines that are prototyping machines, they are expensive, and then they are not accessible to everyone. So with all this knowledge gathered in this time at Aachen, I came back to the lab. We talked, and it's like, we're designers, we are makers. We could turn this fabrication workflow, into a much smaller size that is more friendly, and the people and designers and other enthusiasts could use to customize fibers and to make fibers. So this is the open source Biofibers spinning machine. There is a paper about it for the ones who are interested with like all the more details. But this open source Biofibers machine has multiple parts. One is the hardware on itself. Then there was a lot of also testing in terms of spinning solutions, like material science side, how to make a stronger fibers, let's say, out of gelatin. But we could customize that too. And then finally, the smart textile applications, how we see that working. So here is really all the parts of the Biofibers machine replicates it has a parallel process with the bigger machine. So we have, we use a pump. We use there for the whole frame an old Ender 3, parts of an Ender 3 3D printer. We have a syringe that contains the liquid solution. It's a 60 milliliters, but that could also change depending on needs. There is a silicone heater wrap that keeps the solution warm. Something really, really interesting of biomaterials is that they don't need to be in high temperatures. Like PLA, we need 210, 215 Celsius to extrude. With biomaterials, we only need like 35 Celsius, like right above room temperature, let's say. It's like uses less energy as well. So we have the heated nozzle that also needs to be just a little bit right above room temperature. And we have the collectors that collect all the fibers. And under the collectors, we have the multi-purpose vats. So all of these parts of the machine are modular. You can take them apart and just exchange it for something else that we might need for our specific use. This is good news. We just released last week the beta version for the interface of the machine, because before we were working all in G code, but now we have an interface thanks to Xin Wen, who's part of the team. She's now a PhD student in Michael's Rivera's lab. This is the link to the GitHub that has also a Discord channel. So just to explain customization and why customizing fibers is important. For us, customizing fibers is important because we can decide the material composition. We can decide, what our fibers are made out of. We can work and explore different tensile strengths, colors, and a lot more. So in the interface, we can, for instance, control the spinning speed rate, and we can get different also thicknesses in the fibers that go from 0.03, much thinner than our hair, to 0.20. And when we run a strength testing, we can see that based on its cross section, the strength of a 0.2 fiber, it's like close to be as stronger as PLA in terms of like megapascals. This is like close to 71, and PLA is close to 75, if I'm not wrong. So there is a lot of, I would say, potential also for other applications. This is the second part, which is working with, material preparation, creating the solutions. So this is a natural color of the biofibers, the gelatin biofibers. But we can also customize color by adding like a food coloring to the original gelatin spinning solution. And I have here some examples. If you want to see and touch, they were mainly, customized for testing colors. And then we can also, in the spinning process, we can also add something that is called a cross linker, something that makes the fiber stronger. This is made with genipin. It's like it's a plant-based material that makes the fiber stronger, but not also stronger. It also changes the color from light green to darker green, which was cool to see. And then we can also customize the fibers in the post-production process. Basically, after they are spun and they are rolling in the rollers, we can, in the coagulation baths, we can add some plasticizers to make them elastic, like glycerin make the fibers elastic. But then we also can coat them. For instance, this one has a photosensitive pigment, and we can see that we can also see change in color in the fibers. These are the applications in the smart textiles. So the way that we see them is enabling disassembly by dissolving the fibers at certain conditions. So we have here a moisture sensor that has been woven, a pressure sensor that's woven. There are conductive and non-conductive fibers there, cotton, silver threads, and gelatin in the middle. But then when they are exposed to hot temperature, hot water, not even less than like 80 C, less than coffee hot, I would say, we can, the gelatin fibers will start, getting loose. And then at the end, they will be easy. This was a video, but it would be easy to dissolve. And all the electronics threads or conductive threads will go on one side, the cotton on another one, and we can recycle or repurpose them like properly. Another way that we see that is like in weaving, we have knitting. So now we're talking here about weaving, but in weaving, we have these two layers. And sometimes when we are designing smart textiles, we need one side to be in contact with the skin and another side to be exposed to the outside. So the nice thing about having this two-layer structure is that we can intentionally just expose the area in which we would like to make soldering, for instance, a connection on the body, and then just mend it at the end, but it can be after the textile is on the body. So to wrap up and finish, for us, this open source biofiber spinning machine is enabling biofiber prototyping. That was something that was not possible before. As I mentioned, this was really close to chemists and also material scientists, and in these other labs that we don't have access to. We are unlocking this fiber design space. We don't know what other people might want to do with fibers, right? We only think about smart textiles, but fibers might be used for many other things. And yeah, and we are happy to be part of this growing open source community. But then I would like to point out some challenges, because I wish, I hope in this group, you could know more of like the type of challenges that we faced. Everything was not like nice and happy. So there is kind of like a bottleneck in biomaterials innovation, working with green chemistry, understanding like polymers and working with chemists and how they talk about it. There is a barrier in language, there is a barrier in like a lot of like understanding. So the more we do this work, the more the machine is replicated, and we enable those spaces for discussions, for exchanging knowledge. We think like these right now bottleneck will really open up a little bit more. So that's one of the reasons why we have been working only with gelatin fibers for the past 3 years. Nefeli, who is also part of the team, she just graduated from her undergrad. She was working a whole year trying to make new material formulations with agar, which is another bio-based material, but we didn't get like great results yet for fibers. And interdisciplinarity, as I mentioned, a lot of knowledge from different disciplines is sometimes hard. Future work is to explore more applications and explore and develop modular parts and new functions on the machine, and then continue building this open source community. These are some samples from 3D printing with gelatin fibers that when they go together, for instance, they stack really well and we can have like printed pieces. We're still working on that right now in Michael's lab. And here's the GitHub repository. And then I'm in the job market. I'm graduating from my PhD this year. If you know anything about anything in Europe, please let me know, because I'm planning to relocate. And yeah, and Michael Rivera, who's new faculty in Atlas in our department, he's constantly looking for PhD students. Thank you, everyone, and it's a pleasure to be here. Thanks.